Hello everyone, it's January 14th. Alright, I'm gonna do for tomorrow, and that's gonna be a difficult one. Oh, my heart just skipped a bit. Skipped a bit. Skip a beat. Alright, last time we done that, was bad. 3.5 hours. Now, for one thing, we're not gonna do that. We're gonna try 1 hour, and that's not working. We're gonna check the answer. Check the hint. Alright, given an array of integers, you're initially positioned at the first index of the array. In one step, you can jump from index. Is this in the? That's not in the nightmare. In one step, you can jump from I to index I plus 1, where I plus 1 is this, or where this is this. J, where array I equals array J, and I now equals J. Return the minimum number of steps to reach the last index of the array, so you can not jump outside the array at any time. So in the jump, 0 to 4, 0, 1, 2, 3, 0 to 4, 4 to 3, because I jump front and back, and then 3 to 9. Ooh, nice. One jump. Ooh. So what we're saying is we're gonna minimum number of jumps, right? So in order to jump to the last one, either we have something, then we jump there. So the problem becomes the minimum steps to reach here, or the minimum step to reach here, right? That's the only two possibilities that you go this. Either you're here or here, right? And we have 5 times 10 to the 4. Okay, so now we're trying to solve the minimum number of jumps to reach here, reach 404, right? So to do that, either the minimum to go here or the minimum to go here, or we need to find another 404. There's no other 404. Okay, so now we need to minimum jump here. Minimum jump here is just to see. So for here, because I jump from here, so I cannot go back. So minimum will be go here, or go here. Boom, we hit it already. So is it like a BFS? So I know it's 4, right? So the next one push in is 4. Well, it's actually not 4, but that's 9. So next push one is 8, right? Or 0, 1, 2, 3. 803. Okay, so now 8 pop out because 9 is visited already. So the only thing we can get is no 3, so it's 7. So the next round could be 7. And with 0, 1, 0, 1, 2, 3 with this, we'll find another 404 that's not been used before. Because it's already in there, so yeah, so don't bother. So it's gonna be 0, 1, 2 or 0, 1, 2, 3, 4, right? So these two, okay. Next one, 7 comes out. 0, 1, 2, 3, 4, 5, 6, 7. So 7 comes out. Next one is going to be, can now do this. So 6, right? And then we can do this 5. So 6, 5. And then 2 comes out. 0, 1, 2. 2 comes out. We can do 1. And then 0, 1, 2, 3, 4. 4 comes out. 4 we can do 5, but 5 already in it. Or we can do 1, a 0. boom, we hit it. So we go 1, 2, 3, 3 steps. Let's try this. Let's try this idea. And if this idea doesn't work, we are going to call it because it's very late. I don't want to spend too much time. Tomorrow is going to be a tough day because I want to collect data and yes, I had to spend some time under the sun. And also, like always, there's always training in the morning. So, all right. So we're gonna do our traditionally. We have we need to first produce positions, right? It's gonna be a default dict of list. So we're gonna say from collections import default dict. Okay, and then for I, a in enumerate array, say position a dot append I. Okay. Ooh, append. Yeah, append, which is fine. All right, so visited equals array set minus 1, right? Q equals array minus 1, all right? So while Q, and then res equals 0, right? While Q temp equals this, and then for, oh, shoot, that is not true. That is not true. N equals len array. Okay, so this be n minus 1. N minus 1. Okay. So for I in Q, right? And then it comes out, and then we have two options, right? I'm going to say if we first grab everything in here, right? I'm going to say for if I is equal to 0, then we return res, because I think that's the fastest way we can go. Otherwise, right? Otherwise, I will visit this, right? Otherwise, let me say for neighbor, right? In position. Ooh. Array I, yes. If neighbor not in visited, then we say temp.append neighbor visited.add neighbor. Okay, so done, and then we say if I plus 1 is smaller than n, and I plus 1 not in visited, temp.append I plus 1 visited.add plus 1. Same thing. Let's say if I minus 1 is larger equal to 0, and I minus 1 is not visited, temp.append I minus 1 visited.add I minus 1. Okay, so set everything up. Right, set everything up, and then Q equals temp res plus equal 1. Then, yeah, that shall be it. Okay, let's try this. This one, chart 3. This one, shall return 0, and this one shall return 1. Okay, array minimum jumps. Okay, this one pass. Not sure. Let's run it. Huh. Ooh. Okay. Oh my goodness. We pass a lot. Okay. So why? I mean, it's 7, right? So we have all of them. Do we have like a preference on where to go first? Well, technically speaking, right? Technically speaking, we want to go to the closest to the front. Yeah, that's not strictly speaking, that's not true, right? But why would this take so long? Because 7, neighboring with a gigantic neighbor, and then none of them is in, so temp is huge, right? Temp is huge, and then it came out. It depend on. Wait, hold on. Oh, it takes so long. Because I go here and then I put entirety in it. And when we go for the second round, the first eye popping out, because I have to, first one, so I need 2 steps. And the first step will take a lot of time. The second step will take a lot of time. I mean, this is already sorted. It's from small to large. So when we push it in, it's also from small to large, right? What if I'm not sure. Like, don't do it here. Right, for I in Q. If I is 0, then we'll return rest. If I is not 0, then we always try, right? We always try. If I equal to 0, return this. If I minus 1 equal to 0, because return rest plus 1. That will still be true, and then we can probably end it earlier. That means we don't have to wait for the whole thing to end, right? So the first round, we push everything in, right? And after we push everything in, the first one pops out. The first one pops out as the smallest, so it's -1. Not sure. Okay. Is this like a hack? We got it pass with the little hack. I'm proud of myself. All right, I'm pretty proud of myself for solving this hard problem. The first time I did it was December 2020, and it took me more than 3.5 hours. And I'm pretty sure I had to recurrir. Oh shoot, did you do, oh, screw me, I don't think I did my Spanish today. Oh wait, no, I did. Did I? No, I think I did. Yeah, I did. I studied 66 cards in 4.79 minutes. No, I did. All right, everything's good. Everything is good. All right, we're back here. So I had to resort to the solution. This time I have an ugly solution, but it works. So the ideal is BFS, and BFS. We start from the destination, that is the last index, and push all possible previous step to, in this case we can actually go forward as well. Yeah, we can go forward, it doesn't really matter. All possible previous step to a queue. The shortest path appears once we reach index 0. However, there is a trick to handle a specifically large test case. That is, we always push into the queue from smaller, right? From smaller index to large, to large index, right? We always push it from small index to large index, and each time an index popped out, we always check whether itself is 0 or whether itself -1 is 0. This is because these are the only two possibilities that the 0 index can be reached. Ideally, we shall only have to test the index itself, but to avoid, right, to avoid unnecessary, to avoid waiting for the next round to check index, to check the current index -1, we can check it immediately. And if it is 0, then we save a lot of, then we save a round, save an entire round, which is, this is the difference, right? Entire round. This is the difference between passing OJ and TLE. Yet still, this is a hack. So on, because each is visited once. Or technically O2n, because that's OM. Alright, and we have another here. But each one is visited only once. Alright. $29, not too bad. And this is the hack. This is a hack to avoid TLE. Waiting for the next round. A hack. Alright, so let's see what we have. I'm pretty sure this is the oh wow, 98%. Hold on, 20 test cases. How many test cases do we have this time? I think we have 32. Yeah, we have 32. Boy, it's longer. Much more test cases. Alright, anyway. Okay, it's a graph. Then we traverse the graph. Build a graph. Find the shortest distance from 0 to, deck. Well, this is top left. Notice, seeing the alpha child in graph array. Wait, what is this? We reversed it. And plus this. Why do we reverse it? Oh, yes. We reversed it because then the end comes first. And then we check right here. You see that? We check right here. We do 2 rounds of check. Ah, that's the exact same solution. Exact same solution. And we have these two. Ah, for neighbor in this plus I plus 1, or I minus 1, I plus 1. Not even visited, and 0 smaller equal to neighbor smaller to n. Oh yeah, we can save all these time. Oopsie doozy. That is not correct. How? How is this not correct? Oh, hold on, let me think. Oh, wait. I think it's fine. I don't have to add this. I don't think that's the reason. No, that's not the reason. Okay. 9, 3, 8. 0, 1, 3. And 8, yes. From 3 we have 2, 4. Uh-huh. Oh. So we check I first. Let's check it inside. It's the neighbor, right? Wait, hold on. We need to make sure. And the thing we're not making sure is the smallest need to go out first. How was the previous one correct? Two, 4, 7, right? And we go to 2. Here, 1. Yeah, I don't understand. I don't understand. How is this one? How is this one right? I put +1 first. But still, it doesn't make any sense. Are you saying if I put +1 first and then -1? Huh? That was pure luck. It is not supposed to be. It's not supposed to be. I think, I think, I think I want to make Q a heap Q. So every time pop out is always the smallest thing pop out. I'm willing to do that just so that it will not be wrong, right? Yeah, it has to be the smallest coming out because that's how we check. Which probably is why there's different solutions at the end. That's the other solution. Clear. So here is this, our graph will be this. When we do BFS, we look at node 0 and append this to the queue. Now look at 1, since node 1 and 0 belong to the same value, we don't have to go through this again because these nodes have already been in the queue. In other words, after the first encounter of a value, we can remove all the indices related to the value. Are you saying we don't need the hack? Ah, I think I see. The problem we have is we have to go through them again, Yes. Yes. Okay, so let's keep this one this way. Yeah, but this is not correct. This solution is technically not correct because it depends on the order of adding uh, neighbors to the queue. In particular, if we add I minus 1 before I plus 1, then this solution fails the first test case. To avoid, to resolve this issue, right? To resolve this issue, we need to always pop out the smallest value in the queue, which requires us to use a heap. be a heap queue. However, it also increases the time complexity, right? Time complexity. See a better implementation in solution 2. So this is solution 1. Solution 2 is exactly the same, but we have a little bit. So this is essentially the same as solution 1 and is inspired by my by the solution I submitted more than in December 2020. So the to avoid the impact of order of inserting, so appending to the queue, we should remove the check for I-1 equal to 0. And to alleviate the wasted time we use a trick where the position dict is erased once its value, where the key and value of the erased once the key has been visited. This is because each time, because the first time, right? The first time key is visited, all of its neighbors in the position dict will have ended up in the queue already. Therefore, when these neighbors are visited, we don't have to push any of its neighbor to the queue again. This guarantees that each unique value is only visited. Each unique values position dict, unique value in the position dict is only visited once. So it's still O(n). So we don't need a hack, and doesn't matter. We can go minus, plus, blah, blah, blah. So once we're done, we say position neighbor, array I dot clear. Trick, right, to avoid visiting, avoid position again. Avoid listing using. Okay. Solution 2 work. Then here. Submit. That's slower, but it's fine. Okay, this one, we run that 1083 milliseconds, 16% ranking. I'm actually curious. Let's do a solution 3. Okay, let's do a solution 3. I'm actually curious. Okay, so I want to do solution 3. I want to say it's same as solution 1, but with a heap queue to guarantee correctness. Okay, so what do? I would say when login, we need to import heap queue, right? So what we do is temp this. That's not for I. And this is while queue, right? I equals heap queue dot heap pop queue, right? And then if this is 0, if this is, we do this, and then for this, not append. I'm gonna say heap queue dot heap push temp and neighbor. Okay, so that is you're stupid. How could you be so stupid? Changing the wrong position. Gosh. Alright, it's fine. So just do this. And yeah, I always have this issue. Not the first time that I change in the wrong position. Alright, solution 3. Yeah. And then if we don't use this, this is going to be wrong. Okay, let's try this one. I feel like this shall be I shall run this one first. Yep. This is actually slightly faster. Note that there are 4 more test cases this time than last time. All right, I think we did find the right solution. Good. Yeah, I want to end it right here. Let's take a little bit break. Do we really want to end it right here? Well, I said so, but it's tempting. It's tempting, very tempting. This one, right? Because yesterday we did it. It was not that hard, so maybe it's okay. So longest palindrome by concatenating 2-letter words. Oh man, palindrome? Palindrome. Shoot, what's the KMP? Maybe what is KMP? You're given an array of string words, okay? Each element of words consists of 2-letter lowercase English letter. Create the longest possible palindrome by selecting some elements from words and concatenate them in any order. Each element can be selected at most once. Return the length of the longest that you can create. If it's not possible, return 0. This is an interesting question. Alright, so the longest possible. Alright, here we go. Palindrome, alright? Depending on whether it's if a value itself is palindrome. If the string itself is palindrome, alright, then the only option is either put it in the middle, or if it has a pair. What if it has a pair? Then we definitely, because we can always concatenate them or put them on both ends, right? So if we have a palindrome string, palindrome word, and it is by itself, then it can only be used in the middle. If it's a pair, then that's fine. Right? And if there are 3 of them, always fine. Always fine. If we have a palindrome, doesn't matter. Always good. Always good. So we're going to separate out. So we have the palindrome, we have probably this, and their length. Okay? Okay, so we have the palindrome. Now if we have a non-palindrome, right? If a string is a non-palindrome by itself, then it must have a pair, which is its reverse. If we do have, and each one can only have, we have multiple pairs. Pairs. How many pairs, right? That's what we want, is how many pairs. Okay, so we're gonna search through this, then we find if it's pair. If we do have a pair, then they can always make into palindrome. Yes, they can always make into palindrome. So we call a counter on everything. We call a counter on everything, and we search through. If it's if the value itself is a palindrome, and remember, if it's a value itself is a palindrome and then has even number of repeats, then that just, we can always add it. But if it has odd number of repeats, we're going to record its length, because that's the seeding. We can call that the seed, right? Everybody else, yeah, we can solve this. I think we can solve this. I have an idea. So first of all, we need a counter. Okay, so you say counter equals counter words, right? And then we have res 0 and seed, max seed 0. Okay. Then I'm gonna say for, I don't know, for w encounter. Yeah, it's fine for w encounter. We'll look through the keys. So for w encounter, if w is not equal to, let's see how big is each Oh, I did not see that. There's only 2. Huh. That's fine. So if this is not palindrome, so W is not palindrome, right? If itself is not palindrome, then we need to find its pair, right? So ref W equals, oh, okay, just ref W equals W, this, right? And then we say if it's not equal to ref W, and if it's not equal to ref W, then what we need to do is we're gonna avoid double counting. Set it to 0. Yeah. So if W in is not in rev, if W is not equal to rev W, so it's not palindrome, then we need to check the number that it has, right? So we have, let's say, how many of this, and how many of this, so we can only take the minimum between the two, right? So rest shall plus equal to minimum of counter W and counter ref W times 2, right? So we can take, let's say, 2 of these. Wait, hold on. So we have 1 pair, so times 2, so we have 2, and then times 2, because this is equal to 2. So that's the total, right? And yes, else, blah, blah, blah. Once we're done, we go counter W equals counter reverse W equals 0. All right, now we say if this, or counter W is even, right? If it's even, either they're not the same, or if it's even, we do this. Oh, shoot. No, that's actually not true. Else. Elif, yeah, let's do this. Elif counter W 0, right? So W is palindrome and has even count. In this case, rest plus equal to counter W times 2, because I only have this, right? Else. So W is palindrome and has odd count. So if it has odd count, then rest plus equal to counter W minus 1, I'll make it even, times 2. Which I just realized. And then seed, max seed equals max seed, and oh, it's always going to be 2. They're always going to be 2. Huh. Max seed equals to 2. Okay, then we return rest plus max seed. Wow, let's finish this fast. Yeah, like the first three are not that challenging. But the last one is always challenging. Change the side. Ooh. Shoot. Shoot, shoot, shoot. That's fine. If this encounter yep. Should be max middle. Yeah. Yeah. I wonder if there's an easier way to handle this. I mean, for one, this is fine. This is fine. Right? And these two I want to combine, but I have the seed. Yeah, I guess it's fine. Yeah, I guess it's fine. So let's avoid double counting. Alright, so the idea is that for each word that is not palindrome itself, it can only be used when its reverse version is also in words. If a word is palindrome, I mean, technically we should times len w, right? Technically. And this shall also times len w. This is also len w. This is also len w. That's what's supposed to be. Yeah, that's what's supposed to be. Right. Is palindrome, and then if there are even count of the word, all of them can serve as palindrome. It is the same situation as num palindrome word with its reverse pair. However, if there are odd count of a palindrome word, then one of the word must serve as the seed, right? As the middle part of the resulting palindrome. Now this question restricts each word to length 2, but this is not necessary, and the following solution does not care about this restriction. ON technically should be max, right? Max seed is a technique. So ON, this one runs 1.6 milliseconds. Terrible. All right. I think that's about it. I'm gonna call it counting mirror words. Yeah, exactly. All right, let's see. Unpaired. If this is the same, that's interesting. Not a counter. So for each word, right, so this is a palindrome, and we say if it's larger than 0, then unpaired minus equal 1 is minus equal 1 and 7 plus 4. Else, so it's not larger than 0, so it's smaller or equal to 0. Then we plus an unpaired plus equal 1. Else, if this is the reverse, is larger than 0, answer is this, and Windows this. Otherwise, if there's nothing and this plus equal 1, yes. And at the end, if there are unpaired, so the unpaired is specific to, this is actually good. Yeah, the pair and unpair is an interesting idea. I mean, this is the same idea. Yeah, it's the same idea. All right. Pair and unpaired. I actually like it. I think it's also easier. Paired and unpaired. Like, we don't have to check this. Yeah, and I like it. I like the pair and unpair solution. I really like this pair unpair solution from upvote. All right, so we don't need counter. We can still call counter equals. I can call counter, it's fine, right? And then rest 0, and then we say unpaired palindrome, right? Then for word in words, let's not look at it. So the ideal is if so reverse word, right? If word is not equal to reverse word, then we need to see if reverse word has a counter. When I say if counter reverse word is larger than 0, then rest plus equal 4, right? Rest plus equal 4. And counter this one minus equal 1, because I used it. Else, if counter is not, then counter w into plus equal 1. That is the unpaired. So this is record the number of, unpaired, now record the, how many times each word is not paired, right? So that's that. Else, if it's equal, right? And we say if counter w is larger than 0, rest plus equal 4, and then counter w minus equal 1, right? Else counter w plus equal 1 and unpaired palindrome plus equal 1. So the only difference is these are all the same. And then return rest plus 2 if unpaired this is larger than 0, else 0. Yeah, so it's the same. And then we say if this is this, and counter w is larger than 0, now it's equal to, smaller or equal to 0, then unpaired plus equal 1. I would do this ahead of time, right? And then we do all the others. Okay. So rest equals this. Unpaired palindrome. So actually I can do this. Yep. Okay, let's try this. I suspect it should be faster. I'm gonna go to bed after this. All right, try this. Let's check. Ooh. Huh. Interesting. Hold on. I think this should be at the end then. Nope. So, and then it's not. Right? And then this is not, and this is plus equal 1. And the next one comes in. So the counter is, oh, that we need to remove. Ah, shoot. Compare the minus equal 1. Yep. The other way doesn't work. This one shall work. Yeah, it's alright. I like it because it's simpler. 1758. Yeah. Alright, that's it. I'll see you guys tomorrow for the contest. Adios.